So good morning all to the participants. Today we'll be discussing about the solutions which we as a real-time company provide when we are working with the various power electronics simulations. So I request the participants that whenever they have any doubt related to any thing, you please feel free to ask me at any given point of time, so that your questions can also help the fellow participants also, and it will also keep the session very lively. So the topic which we'll be talking about in detail is the solutions to power electronic simulations, faster and accurate testing in real-time simulation environment. The main thing, if consider that if we are trying to simulate an electric vehicle, so for an electric vehicle, we have like various components which we need to go in the simulation stage. As we can see that the various components which might include in the electric vehicles are the motors which we need to simulate, the power electronics, batteries, mechanical drive modeling, and controllers. But one thing which we need to see is that in all of these in the simulation of all of these components, I have written a number corresponding to it. So this number actually represents the time the simulation should take to replicate the proper Simulink model. So if we see that if you are working with, say, if you're working with a power electronics converter, because of the advent of the new semiconductor wideband devices, the simulation it needs to run at a very high switching frequency. Whenever we are going for the higher switching frequency end, we need the simulators or the host PCs which we have, or laptops, or whatever the workstations. We need such processors to be sufficiently able to simulate such components in their time range. So this is one of the very critical factor which we need to consider when we are working in the simulation of any component as such, not only just the electric vehicle. We need to understand the physical nature of the component which we are trying to simulate, because it is the physical nature. Because say when we are working in the mechanical domain, the moment of inertia is not is very high. In that regards, the time step can be like in the seconds range. But whereas when we're working with high PWM pulses which we need to generate, so at such instances, the time step will go into the range of nanoseconds. So whenever we are working with any simulator, any real-time simulator, the time step factor is always the best, is always the most important thing which we need to take into picture. Now, the main challenges which we see in the real-time simulation, obviously we'll be also talking about that what exactly is the real-time simulation, how exactly is this real-time simulation different from the offline simulation. We'll see that, but before that, just as a brief challenge which we see in the real-time simulation is that whenever we want to interface a simulated model with real hardware component. So this means that let us say that you have your power electronics converters you have developed in a physical world, and you want this particular power electronics converter to be integrated with some software where your controller is sort of platform in which you can go for the interfacing, where one part of your model is in the real world, whereas the other part of the model it will be in the simulation world. So this is the main area. I mean, this is the main reason that why the real-time simulators they come into picture. The next is the simulation of power electronics converter at high switching frequencies. This is also one challenge, and the solution which we also provide as a company. Then the accuracy of PWM generation. So what exactly this means is that we'll even show this thing with the example that when we are trying to generate the PWM pulses by the best offline platform, say Simulink. So if we're trying to generate the PWM pulses, we'll observe that how the time step factor plays into picture, and it leads into the inaccuracy of the PWM generations. So in order to increase the accuracy of PWM generations, we need to understand how these things can be done and how we provide a solution in achieving the accuracy, in achieving higher accuracy for the PWM generation. And as a last challenge, which this is actually not a proper challenge, in the regard that we all know that NPCs, MMCs, these are the various topologies which have been like very widely accepted in the industry. Now the thing is like for a research person who is very new to these things, so what they need to do is they need to first study the MMCs and then try to develop the entire picture of the MMC into the offline platform. So this near about takes some time for him to understand and to develop the all of these models by himself from the scratch. Now, if we just say that yes, there is a solution already which is provided, in which you need not worry about developing the model, developing the controller of the MMCs. That solution is provided by to the research, and then they can directly implement whatever their controlling algorithm or whatever their research objective is, so that there is this time which has been saved of the research people. So this is one of the solution we provide for the MMC topologies also. Now coming to the very basic question is that the three W's which actually correspond to the real-time simulation. These are like what, where, and why of the real-time simulation. So we need to understand that what exactly is a real-time simulation, what is the real-time simulator, why do we need to use this, and where exactly we need to use this. So as a case study, what we have taken over here is that this is one schematic diagram of the hardware setup which has been done by NIT-Rourkela. So this is the hardware setup of NIT-Rourkela. So what they wanted was they wanted to develop a regulated wind power generation system. So for this particular setup, if we see from this particular diagram, we see that they had their doubly-fed induction generator and then their DC motors, so which was replicating a wind turbine. And then we had back-to-back converters, AC-DC, AC converters. We can see that we had these converters connected to the rotor side, and then we had our DC link to which again an inverter was kept, and the output was directly connected to the grid. This exactly was the entire thing which had been developed in the real time by the NIT-Rourkela people. But if we see in the middle over here, we see that there is a box which is called as Opal RT simulator. So what exactly NIT-Rourkela had done was that they had actually used the Opal RT simulator to be used as a controller. So if we focus that, we can see the values of the currents have been taken from the CTs, and then the values of the voltages have been taken from the voltage transformers. And these values, they have been fed into the Opal RT simulator, where the controller was sitting. The controlling algorithm, it was sitting on the Opal RT simulator. The controller was being executed, and it was generating the results of PWM. We can see these PWM pulses which have been generated by the Opal RT simulator. It has been generated, and they are then fed to these AC-DC converters. So this example kind of shows us that okay, yes, where exactly we can have a real-time simulator. In the hardware, in this experimental pic which we have, we can see the same setup. So this is their wind turbine emulator. They had their DFIG motors which was acting as the wind turbine. Then they had their AC-DC AC converters over here. Backside of the computer, they had these voltage and current sensors. And this is where they had kept their simulator. So we can see if the participants are completely new to the Opal RT simulators. So this is exactly how a real-time simulator actually looks like. So we can see from this figure that all the pulses they have been like generated from the Opal RT simulator, and these pulses then can be seen on the DSO. So we can see how the integration has been done between the hardware and on the simulation side. So in this particular example, what we saw was the example which we have studied of the NIT-Rourkela. They had the plant which was on the physical side, whereas they had their controller which was in the simulation board. So this is exactly the case which we define as a term which is called as rapid control prototyping, or more generally it is called as RCP. So in RCP, the main purpose is that we need to test the algorithms of the controller. We need to refine the algorithm parameters, and obviously we need to connect the simulated controller to a real plant. So this is the case of RCP, where we have the real plant on the physical side and we have our controller on the simulator. Just as a vice versa, like someone can also ask me that I mean, they can say that I do not have a real plant. So let us say that we are working on the grid. So grid is not a thing which is like easily accessible. So if in that case we just say that okay, I do not have a real plant, but yes, I have the FPGA with me or any or DSP board. Can we do that thing also? So yes, the vice versa condition to RCP is also possible, and this is what is called as hardware in the loop. So this is you must have like also it is a very general term as of now, hardware in the loop. So what hardware in the loop does is that the plant is now on the simulator. The entire mathematical modeling has to be done on the simulating platforms, and then the mathematical modeling will be run on the real-time simulators. Now, this particular simulator, which have our real plant, will now be integrated with the controller, which is on the physical side. So this is what is called as hardware in the loop. Purpose because it is very safer to test the controller because there are no power signals. They are only the signals which we are interfacing with. They are in the ranges of if you are talking about current. So current is in the range of milliamps only. So the conditions of testing are very safe, and then we can also prepare the final physical test. Uh, as an example to the HIL platform, we see over here that in the Jadavpur University, what they wanted was they wanted to develop a heavy water reactor. Now, obviously, heavy water reactor in itself is not very feasible. So what it was done is, in the heavy water reactor case, the simulator was being replicated as a plant model for the heavy water reactor, whereas controller it was on an embedded target, and we can see that this controller and the real-time simulator they were exchanging information through the IO channels. So this is what is also called as HIL. Uh, so till now, what we have done is we have understood that, okay, where exactly we need to go for the real-time simulators. So now the question arises is that who exactly needs a real-time simulator? It is like kind of same only. So those who have to integrate some hardware with the simulated model. This is one the case which we have already seen. As in the case of NIT-Rourkela, they had their plant on the physical side, whereas the controller was on the simulator, and this condition is called as RCP. Whereas in the case of Jadavpur University, they had their heavy water reactor on the simulator, whereas they had their control on the hardware. That particular case was called as hardware in the loop. So this is the main thing that why we need a real-time simulator. This is that whenever we want to integrate a hardware with a simulated model, then comes the example that those who want to send physical signals between two simulated models. So what it means is, now let us say that in the cases what we have done is we've already seen that one part of your model is on the hardware side, whereas another part of your model is on the simulator. But let us uh, consider the case that we have two simulators. Now, in one simulator, we have our plant, and in another simulator, we have our controller. Now, there is no such thing as hardware for us. Everything is in the virtual mode only, in the simulation mode. But what we are interested is we want to understand how the information is flowing. Let us say that if I'm from the power system backgrounds and I want to understand the communication protocols. So let us say I want to study IEC 61850 or IEEE 37.118. So if I am interested in studying the communication protocols, so this is one case where we have simulated models which is running on the two different simulators, and then the information between those two simulators can be sent through real physical signals. This is also one case study where a real-time simulator can be used. Then those places where having physical replica of systems is not feasible. This is the case we have already seen, as in the case of Jadavpur University, that the physical replication of the heavy water reactor was not feasible. So in this particular case, we can use the simulator to mimic the behavior of a heavy water reactor. And then lastly, those who would also like to execute simulations at a faster rate. So what it means is people actually get confused that when we're working with real-time simulators, so sometimes it is being misconceived that a real-time simulator gives a very faster results. Though in this particular point, yes, it is written that those who would also like to execute simulations at a faster rate. So what it actually means is that if anyone has like tried working on any power system models, so the power system models are very big, and when we ask the MATLAB to run even for say 10 seconds, so sometimes those simulations, depending on the complexity of the model, it takes say somewhere between 1 hour, 2 hours, 3 hours. So even though it was 10 seconds in the offline mode, but the actual time it took was 3 hours, 4 hours. That is why our simulation, the execution rate is very slow. But when we execute the same power system model on the real-time simulator and we ask it to run for 10 seconds, when we come on the real-time simulator and when the real-time simulator executes that power system model, it will actually take 10 seconds only. That is why we can see that yes, whenever we want to execute the simulation at a faster rate, this is also possible with a real-time simulator. Uh, till now, what we have understood is that okay, where exactly we need to use the simulators, and kind of also understood the various places where we can use the real-time simulators. But the main question which always arises is that how exactly a real-time simulation is different from an offline simulation. So this is one major question which we always face. So let us try to understand. Now we are working on RCP case. So we have our real plant, and then we have our controller, which is sitting on the simulator. Now the thing is that let us say that the real plant, it is able to send us one sample per second. So this means that if we are interested in sending the information for 10 seconds, we will have 10 samples after the end of 10 seconds. Now for proper testing of the real plant with the simulated controllers, we need the real-time simulator to also send us 10 samples after 10 seconds. So this means that we also want the real-time simulator to send the data at one sample per second, so that the real plant, which is also sending the data at one sample per second, we have a synchronization between the real plant and the simulated controller. So this is what we are trying to see. That for the real plant, it is sending the data at one sample per second, and its speed is same as the real-time clocks. What it means is that at each second we'll have the data being sent by the real plant. Now we try to understand that why exactly we need a real-time simulation. So instead of a real-time simulator, let us just try to integrate a MATLAB model with a real plant. Though it is not physically possible that we can integrate a real model with the MATLAB, but just to understand that how exactly the real-time simulation is different from the MATLAB, let us consider this particular case. Now, initially we had a real plant which was working at one sample per second, and it was sending a total of 10 samples. So this is what we actually want, the sample rate to be 1 second. Each second have sent by the real plant. Now, what we had done is we had asked that we send us 10 samples. But because the MATLAB is having a controller, let us say the controller which you have developed is a simple paint controller, it will hardly take any time to available. So I'm actually expecting the 10 samples if we just compare the results of the MATLAB with the real-time clock, we can see that since the model is very less complex, it has sent us 10 samples, but the rate at which it has sent the samples is very fast. Within 1 second, we were able to receive all the 10 samples. So we have 10 samples per second. So it is also sending a total of 10, and this is also sending a total of 10. But there is no synchronization between the real plant and the offline platform. This is where the real-time simulators, the basic objective of a real-time simulator comes into picture, because we need to, at the end, when we need to go for the proper testing, we need to ensure that the synchronization is achieved between the real plant and the simulator. So what we do is, uh, the real-time simulator, we do its setting in such a way that we tell the simulator that you also work at 1 sample. And since our real plant is already working at 1 sample per second, and when we try to see the samples which are being generated by our simulator, we'll be able to see that the speed at which the real-time simulator, the rate at which the real-time simulator sends the data is in synchronization with the real data is being collected from the physical side. So this is like the very basic difference between the real-time platforms and an offline platform. And coming to the last part of the introduction, so I have like already discussed a bit about HIL and RCP, but I assume that the participants, they must have also came across the term which is called as PHIL. So what PHIL means is, it is called as power hardware in the loop. So till now, I mean, hardware in the loop, we have already studied that for hardware in the loop, we have one part on the simulation and one part on the physical side. But when power term comes into picture, what it means is, so if you try to consider that example of a battery, if we see from this figure that we have a battery over here, and we need to charge this battery. So we need an actual battery current. We do not need the current in the range of milliamps. We need the current in the range of amperes actually. So what we are trying to do is, in the simulator, our model sits, and from here the simulated battery current will we can extract this information from the real-time simulators, and this information, the information of simulated battery current, it will now be it will now be fed to a power amplifier. Now what this power amplifier will do is, it will magnify the current, whether it is current or voltage. So what it will do is, it will just amplify the signal which it is receiving on its input side, and at its output will have an actual battery current which will have a higher magnitude. Now this particular magnitude will charge the battery. Now what we need to do is, our objective is that we also want to like understand how the controller will work. So what we are doing is, from milliamps we have came to amperes because of a power amplifier. We have charged our battery, and then we have extracted this information, the information of battery voltage. Now this particular information say that it is also beyond the range of the cards which are present on the simulator. So what we need to do is, we need to use the sensors and do its setting in such a way that whatever the information the sensor is sending into the real-time simulator, it should be the allowable range. Because if the signal which is being fed directly into the simulator is beyond the range of the upper limit of the cards which are present, then the cards may go faulty. So we need to ensure that yes, whenever we are working, we need to send the signals in the optimum range only. So this was all about the introduction, where we had like studied about HIL, PHIL, and RCB. I tried to show the basics in the research institutes, the real-time simulators they have been used. And from here, we'll move a bit towards the solutions which we provide as a which we provide for the high frequency simulations. So if the participants they have any doubt till now, we can have a small discussion. I'll wait for say 30 seconds. If not, then we'll continue the session from here. Okay. I assume there are no doubts. So what we'll do, we'll try to understand that if we have a real-time simulator with us, this particular concept over here, what it shows is that how exactly we can integrate a real-time simulator with a host PC. So what we need to do is that a host PC is where we have our MATLAB which is running, and we'll develop our simulations. We can develop simulations on the host PC, and this particular host PC is connected to the simulator through a LAN cable. So this is exactly where the flow of information will be transferred between the host PC and the real-time task. So this is just about the physical connection we need to do. Now the thing is that we all know that this is our host PC, and if we see from this particular thing that this is the graphic interface which we can see, and then we have our various architectures. We have developed a power system, whether it is in the form of an algorithm, whether we have physical signals, or whether we have used the SPS libraries, or like if we have used the various toolboxes which we also provide. So all of this particular information, it will be made to run on the real-time simulator. And if in case, like whenever we work with the MATLABs, so we can, if we're interested in observing a particular signal, so what we generally do is we just keep a scope. Now the thing is, one may also ask the question that yes, now what we are trying to do is, I'll just open the paint. I don't know if it will be visible for all. Just let me know if the paint window is visible. Can someone please confirm that if my paint window is visible?
No, it's just showing the PPT.
Yeah, it's PPT only. I have kept that settings like that. Can you please help me how to change this particular sharing? Do I need to like stop the sharing first and then again do change the settings?
Yeah, in the bottom line, you can see there is some stop video, and the next one is the share. Just click on that.
Yes, yes.
It will
Just one second.
stop
This
share.
software is new to me. How do I like
But
maximize this?
if you will stop sharing, then we will not be able to see your screen as well.
Yeah, that is okay. I'll share my screen again.
Okay.
Yeah.
So
Can I like how
let
do
me
I?
see that. It's not showing any option.
Okay, I think
Okay.
it has. Yes, it has come.
Should I give you the rights to again you again?
Yes, please. Yes, please.
Okay.
Yeah, I think now everything is visible, I guess.
Yeah. Now the paint is
Thank you.
open.
Thanks. Now, what I'm just trying to do is the main things which we do is that this is our MATLAB force. So this is our MATLAB where we have developed our model, and this is where we have our simulator, right? So we have a simulator over here, and as I have told in the PPT, what we need to do is in order to make a connection. What we are trying to do is in order to make a connection between the host PC and a real-time target. So what we do is we keep an Ethernet connection. So if I just show this wire as an Ethernet connection between these two things, so this is what we are trying to do. So we have developed our model. So somewhere over here in the MATLAB, we have our model over here, and we need to transfer this particular information to the simulator. But because what we want is we want the offline model, the MATLAB model which we have developed, we want that particular model to run on the simulator. So the very simple thing which we do is that in the MATLAB model, so what generally is being done is we divide the entire model into uh, uh, we make the entire model into one subsystem, and we call that particular subsystem as master SM sub master subsystem underscore. We can give any name for our own understanding. So let us say I give the name as master only. So when we do this particular thing in the MATLAB, this particular denotion, what it does is it will tell the MATLAB that okay, if this particular subsystem is called as SM, so what it will do is it will transfer the entire code which is related to this particular subsystem, and this entire code will be transferred to the simulator. So this is how we ensure that though everything which is being developed on the MATLAB is getting implemented only on the simulator. So by only making the subsystem calling as SM, we are just transferring the entire code generation from the MATLAB to the simulator. Coming back to the presentation, so this is what I am actually trying to show you. We have a workstation over here, and then we had a LAN cable which is transferring the entire information from the workstation to the real-time simulator. So we have a real-time simulator, and say for example that in a real-time simulator, we can see that what we are trying to do is we have developed a grid on the real-time simulator, and the controller of this particular grid is in the actual hardware for us. So this is the actual system for us. We can see in this particular example the industry study which is being done by the ABB. So we can see the color mapping. So the workstation represents over here. The real-time simulator is over here. So this is where they have actually developed their model, and then the entire controller was on the physical side. So this is how the entire integration has been achieved between a workstation and a real-time simulator and a controller. So these are the same things just the thing which we are to do. In another case study for the IIT Jodhpur, what they wanted to actually do was they wanted to develop a DC microgrid in the real time mode. So what they initially did was their objective was that they had their hardware initially in the simulation mode only. So this is PV array 1, PV array 2, PV array 3, and then they had their DC-DC converters related to all of these things. Now these particular the plant and the entire plant was on the simulation, and then they had their energy management system also. So this was also in the simulation only. If we try to just see over here, yeah. So if we see in the stage 1 of implementation, we observe that their entire plant, we can see on the downside, their entire plant was working on the real-time simulator, whereas their controller, the energy management system, it was also initially working on the simulator. So this is what generally is being referred as processor in the loop, or more commonly it is also referred to as software in the loop, because everything is in the software side only. That is why it is being called such as like processor in the loop and software in the loop. After they had like implemented the stage 1 of their testing, what they did was they wanted to go for the control prototyping of the DC microgrid. Now their physical side, I mean their converter side, is now being transferred into the physical in the physical world, and we can see they had their entire DC-DC converters and their sources on the physical side, whereas again they had their energy management system, which was being dumped onto the real-time simulators. So the RCP stage of the DC microgrid was being done by the IIT Jodhpur people. Another case of NIT-Rourkela, this is also like the same objective but a different setup which NIT-Rourkela had done. Again, the objective was to develop a DFIG controller for a rated wind power generation system. They had their entire physical side I mean, they had their entire power plant model on the physical side, whereas they had the OpenRT simulator in which they had the controller working. This is the case of the RCP, where the controller was being made to test. In another case of the real-time microgrid simulation, so this is kind of an interesting study also. As of now, in this particular figure, what is being done is that the entire microgrid model. So there was this grid, and then we had a wind turbine system which was connected to the grid. Apart from wind turbines, we had the solar also, and we had the batteries also. Uh, on the load side, on the load side, we had the residential loads, and we had some critical loads as well. So another feature of this particular model was that if we want to make this model work on the islanded mode or in the grid connected mode, we could have like done this particular study also. Apart from this, various fault cases were also studied onto the grid distribution network, which was also connected to the grid, and we could have like observed that how the various faults on the transmission lines would have impacted the power generation from the renewable side. So if time permits, we can always go for the live working of this particular model, and we can see with a very with the lab view GUI, we can see that how the entire uh, power is being transferred from the source to the load side. And, uh, considering Mumbai. So what they had done is, as I already told, that not only the plant or the controller can be made to sit on the simulator, what we can also do with the help of real-time simulators, that we can also study the various communication protocols. So these are various protocols we also provide, and these are the various protocols such as DFIG, IC6 IC61850 Goose, and Modbus C37. These are the various communication protocols which are also being configured. Their drivers have to be initialized, and then the entire testing on the communication protocols can also be done. Another case of the application is it is kind of same if we just see that the plant is on the physical side, and from the plant we were sensing the information, the IOs, they were taking the information and feeding the same information into the OpenRT simulator. So this is like kind of the case of RCP, where our controller is sitting on the real-time simulator. So till now, I mean, more or less we have like just covered about the where exactly the real-time simulators are being used, and how exactly the real-time simulation is being different from an offline simulation. So this sets the platform for us to study that how exactly with the advent of new wideband semiconductor devices, where the demand is that we need to test the entire converter at a high switching frequencies. How do we actually solve those particular things? So as a company, the solution which we provide for the processing of high switching frequencies is called as EHS. So what exactly EHS is? It is called as electrical hardware solver. Now this is one kind of solver, and the entire development of this particular solver has been done on a research paper. So this is like a whole different thing. But the main thing what we need to understand is this is like we all know that why exactly the high switching frequencies are required. If we see on the right hand side, if the PWM pulse is on the top, they are like I think 1 kilohertz, and corresponding to 1 kilohertz, if we see the load currents, we can see the ripple in the load currents. But when we increase the switching frequency from 10 to 100 kilohertz, so I mean whatever, whereas in the case we can see the PWM is now being generated at 20 kilohertz, we can see the current profile which we are observing. It does not have those many ripples which were there in the earlier case. So we know that with the high switching frequencies, the various benefits which we have is higher power density, lower THD. But the main challenge which comes onto the real-time simulation is that because when we want to work at a very high switching frequencies, so this is the case when we like need to understand that because we are working at a high switching frequencies, this corresponds to a time which we call as 1 microseconds. This is the time. So generally, if most of the people they also come up with the doubts that how do we actually use I mean, how do we actually evaluate time step values? Because we at times we just give the random values, and this actually creates a problem. So as a solution, if I won't say a proper solution, but a test guide for that will be like if we just try to see that I say that okay, the maximum switching frequency of my model is let us say that it is say 10 kilohertz, and we all know that the Nyquist criteria what says is that in order to do this Nyquist theorem, I mean in order to be compatible with the Nyquist theorem, what it says is that the sampling frequency should be at minimum it should be like twice highest frequencies. So what it says is that now we know that our model which is running at 10 kilohertz, now for accepting the Nyquist theorem, what we want is we want the sampling frequency to be at 20 kilohertz. But there is a problem with 20 kilohertz. Let us say that yes, I went ahead with 20 kilohertz, and uh, our maximum signal was at 10 kilohertz. Yes, we'll be like able to like follow the Nyquist theorem. But the question which arises is that will we be actually able to save? I mean, will we be actually able to receive the same signal or not? So that is the main question in hand. So if in case let us instead of say 10 20 kilohertz, let us say that I want to generate a 50 hertz frequency, sine frequency, and for 50 hertz, as per Nyquist theorem, what we need is we just need a 100 hertz sampling frequency. What it means is that if I'm like trying to get a sine wave, this is actually my waveform. So if I just roughly draw it, this is how my sine wave should look like. So this is going to 50 hertz. Now Nyquist theorem says is that the sampling should be done at 100 hertz. So what it will say is that you please collect the sample in these particular positions uh, at 100 hertz. So this means one sample will be taken over here, another sample will be taken over here, and then another sample will be taken over here. Now this is going to be, and then because this is 100 hertz, this is going to 50, this is going to be 100, and then we will have one sample over here also, and then we'll have one sample over here also. So these are the samples which we will actually take when we are working as per the Nyquist theorem. So this is actually going to create a problem. We see because we wanted a sine wave, but because of the Nyquist theorem which we have taken, a 100 hertz sampling frequency, what it will do is instead of a sine frequency, what we will actually achieve is we are going to just receive a triangular waveform. So we see that the theoretical answer for achieving the time step is not very much compatible. So what we need to understand is that yes, when we want to make a 50 hertz signal, a 100 hertz signal will not be the right choice. So as a rule of thumb, and also as a further study, what we do is that we take the switching frequency to be at least best thing, if I would have to make a guess is say this is 50 hertz. So for 50 hertz, we need say 1% frequency. It has to be like 100 times more. So at least as a rule of thumb, the switching frequency which we take which we need to take is it should be roughly around 5000 hertz in order to perfectly get our simulation answers depending on the highest switching frequency which we have in the model. If yes, if we have 50 hertz, then choose the switching sampling frequency to be 5000 hertz. Coming back to the topic of EHS, this is like what we have already seen that yes, we want to work at a very high switching frequencies. So we know that yes, the switching frequency should be high. But the question which again arises is that whether the processors which are there in the real-time simulator, whether those processors will be able to simulate our model at such high switching frequencies. So this actually creates a very challenging problem. And as a solution, this is uh, the solution to this is that in place, I mean, in the simulator, obviously there is a CPU processor, but even the speed of the CPU processors is not that much enough that we can simulate the model in the range of nanoseconds or in a very high frequency range. So in such cases, when we want to simulate the models at a very high switching frequencies, the processor which we are going to use is a FPGA processor. We can see from this particular figure that the solution which has been provided for high switching frequencies, the solution which we provide is EHS, which is called as electrical hardware solver. So we know that okay, there is this one concept which we are using in order to make a solver which is being called as EHS. But now the question arises is that the entire code of the EHS, whether it is going to run on the CPU processor or is it going to run on the FPGA. So the answer is because we want the clock frequency to be very high. So that is why EHS, the electrical hardware solver, is being made to run on the FPGA. And the other main thing is now we understood that yes, we need to make use of the FPGA. But a question which might also arise in certain minds is that whether if we are working with FPGA, do we need some expertise on the FPGA itself? Do we need to learn the VHDL programming or any other things which are related to the FPGA? So the answer is no. The only thing which we need to do is there is when we install the softwares which are related to the Opal RT hardwares. So whenever we use you install the softwares, we will have a entire library of the Opal RT which gets integrated with the MATLAB library, and and from that particular library, all we need to do is we just need to choose the block which is called as EHS. It is as simple as that. So from the EHS block, we dump our converter model into that particular subset. That the MATLAB knows yes, the user is trying to tell that please run that power electronics converter model at a high switching frequency. So this is as simple as that. From this figure also we can see that initially what I had told you was that the host PC had our MATLAB software where we designed our model. Now this entire model was being dumped onto the real-time simulator through the Ethernet cable. But within the simulator, as we can see, we had a multiple core CPU, and then we have an FPGA which will simulate our electrical hardware solver, which is the solution for the high switching frequencies. And then we have these IO boards. So these IO boards are the boards which will be used to transfer the information, whether it is the information which you are transferring the analog kind or whether the information is of the digital kind, whether we are receiving it, whether we want to send the signals out from the simulator. So all of these IO boards, they'll be being made to use actually. And within the simulator, we have the we have the CPU processor, which is multiple core. So what exactly is the benefit that when we are going with the multiple core CPU is, what it means is like initially what I have told you is that we have our MATLAB over here and then we have our simulator over here. Now, in order to tell the MATLAB that you please run the entire architecture which we have developed on the real-time simulator, so what we do is we make a subsystem and we call that particular subsystem as SM. So we are calling this subsystem as SM. So this naming of the subsystem will tell the MATLAB that you entirely run the code of the model which is there on the subsystem called as SM onto the real-time simulator, and this entire information is getting transferred through the cable. Now what we are doing is, so what we have done is this SM has now come into this simulator over here. Now, the main thing which comes into play is that this is a real-time simulator if I talk it in a bigger way. And what we have is within the simulator, we have the CPU. So let us say this is on the left-hand side, we have the CPU, and on the right-hand side, we have our FPGA. This is our CPU over here. And let us say that this is our FPGA. Now, the question which arises is that, okay, though we are talking about high switching frequency solutions, but let us say that we are also interested in the power systems also. And generally with power system, the solutions, the models, they become very big. Because the system, power system models, they do not need high computation time. So what we do is we'll run the power system model to the CPU only. Or the CPU will run system model. because we do not need such high computation time. But the power system model is static. Now, in order to solve those big models and make them compatible with the real world, what we do is we have the CPU, which is not a single core CPU. We have a CPU which is multiple core. So instead of one, say we have just say that we have four core CPU. So what it means is that the initial big model which we had of the power system, now this entire model over here, let us say if this is our entire model. So what we can do is we can subdivide this model into four parts. And what we'll do is we'll ask that you run this particular part on single core of the CPU. You run this particular part of the model on another core of the CPU, and similarly like these things. So what this will do is all of these cores, they will run in parallel. Now, because these codes are running in parallel, initial model which was where even for a real-time simulator to solve. So what we are trying to do is we are trying to break the entire model. We are trying to decouple the model and then make the entire model run onto the different CPU cores. This is the main advantage of having a multiple core CPU. So I hope this point is clear to everyone. This is what is also in this one. That we are designing a power electronics circuit over here. And we have a CU model, as in case of the power system, which is a FPG. We can develop a slower part onto the CPU, and we can develop the power converter models which are running at a high frequencies on the FPG. And the last thing, if we want to say that if you like connect real controller with the simulator, so obviously we have the provision of IOs and real controller. This is with a real controller. So this is what I was actually trying to convey earlier. When we want EHS to be used, we need not go for the learning of EHS. I mean, of the FPGA. So what EHS in itself is, it is just a black box over here. So we can see this is one particular block wherein we will have power electronics model. So we can see simply by just like keep file name of the power electronics model. We can tell the MATLAB that yes, we want power electronic motor to on the EHS, which is having a high switching frequency. So if I have, I think I have MATLAB open, I can one second see show you like how these blocks look. I'll just open the map and even I'll show like after we install the software we actually use in order to compile the results is called as RTLab software. So if we see over here, this is how exactly the RTLab software actually looks like. So this is the place where we keep our model, and then the entire modeling, whatever the process is, this is like a whole different thing. But yes, so we keep our entire models which we want to run the simulator. So after we keep the models over here, the entire information building of execute model, loading the model, uh, biggest time step. So whatever we are interested, the entire information comes on to the right hand side of this one. So this is a platform called RTF software, which one can directly website. Just give me one time. The library to open. If participants they have any doubt, I did not have time to see the chat window. So if any participant has any doubt, then please talk about. Okay, I think it is taking some time. It gets open. I'll like continue to present and show that how exactly the HS blocks actually looks like into the Simulink library. Now, what we understood till now is that yes, there is a solver which is called as electronic solver, which is on the FPGA. The reason for choosing FPGA is very simple because FPGA processors have a speed which is very high as compared to the CPU processors, and because we want to achieve the switching at a very high frequency, that is why we are going to make the EHS run on the CPU. Oh, sorry, on the FPGA. Now, the thing is, what exactly an EHS itself is. If we try to see over here, so the main thing, the method which an EHS solver uses is it is called as a Pijovic method. Participants, if they are more interested in understanding how exactly this Pijovic method solves the non-linearities, is that they can go through the research paper over in the IEEE Explore website. So in the Pijovic method, what exactly is being done is that whenever the switch is being made to run, whenever it is in a conduction stage, it is made to behave as an inductor. So we can see over here, whenever the switch is in the, it is being made to it is being made to uh, being replicated as an inductor, whereas whenever the switch is in the blocking mode, it is made to behave as a capacitor. So this is like the major concept which is behind the Pijovic method, because whenever we deal with the uh, whenever we deal with the semiconductor switches, we need to consider their known linearities into picture. So Pijovic method, they remove the non-linearities in the way that whenever the switch is conducted, the switch is being replaced by an inductor, whereas whenever the switch is in the off condition, it is being made to run. It is being made to behave as a capacitor. So this is one case of like this is one case of removing the non-linearities of the semiconductor switches. Also, the what MATLAB also does from their own solution is if we open any power electronics converter, if we open any semiconductor block from the Simulink library, if we see that we can make the semiconductor switch to be operated in different modes. So one is called as switching devices, one is called as switching function, and one is called average controller. So these are just the ways so that whatever the user is actually interested in. Say that whenever we are working with the power system modeling, at that particular stages, we are not interested in the transients. We are like, we just want the switch and we just want the average value of it. So this is one of the situation where the semiconductor switch is being made to operate as an average kind of thing. So again, it depends on the user's point of view, the application point of view. They can make switch to operate in the different modes. So this is between of EHS. So how EHS is simulating is it uses a modified nodal analysis as an approach to calculate the system equations. It solves the conductance matrix of the network to find the voltage at each node and the current from each source. The main thing which we need to understand is that since EHS is working on the FPGA, so there is a limited amount of space available. So depending on the FPGA which we are using, there will be a limitation on the EHS. So we can see over here the maximum size of the circuit which we can actually implement on an EHS. It is actually determined by the number of inputs, number of switches, and the number of reactive components. These are like the number of LC components we have in our circuitry. So it again depends on the user's point of view. Like one of our recent prospects, Anna University, what they wanted to do is they wanted to study the impact of EV charges. If all of the EV charges, they are like made to switch on together. So there will be a huge amount of power being demanded from the grid. So how that particular power demand will impact the quality of the power of on the grid. This is what they want to do on a study. Now, the main question was because they wanted to simulate, say, 50 to 100 charges, and 50 to 100 charges because they wanted to also study the harmonics. This means that they wanted to make the semiconductor switch function as a switching device. They did not want the model. They did not want the semiconductor switch to be behaved as an average kind. So this is again because their objectives were clear, that they wanted harmonics to be studied, and their number of components, they wanted to study say 50 charges. So these kind of restrictions tell the user that whether a particular version of the EHS. So say like if we are going, because there are various versions such as EHS 32, EHS 64, EHS 128. So it again it all depends on the user's application, so that they understand that okay, yes, if I want to do this study, I need to have this particular sort of toolbox available with me. We can see that one FPGA may have several EHS cores, where each solver can simulate up to 72 switching devices. This is like just the further information, so that whenever if any of the participants is interested in understanding the capability of an EHS, they can have that particular information with them. This is like the EHS library which I was trying to show. Meantime, I guess the library will be also open. So over here, if we go, so we see that my Simulink library is a bit different than yours. We can see the various toolboxes which are present because I have already installed the RT-Lab software. So we can see that there is this one solver called as Artemis. Then we had a solver, a toolbox called as EFPG system, RT event. These are various toolbox depending on the application on which we are working. So since I want to show to you the ES block, so you can see this is the ES block just trying to show. So as I told you that what it does is it is just a black box for us. What we need to do is we just need to open this particular block, and the power electronic converter model which we want to simulate at a high switching frequencies or in the nanoseconds range. So all we need to do is we just need that particular circuit file name to be added at this particular position, and it will automatically take that how many number of switches are present on the simulator on your power electronic model, how many number of inputs are there, how many number of outputs you want to measure. So the entire information regarding the inputs, regarding the gating pulses, and regarding the outputs which we want to see, all of these informations will automatically come after we just upload the circuit which we want to implement at a high switching frequency. So the things are very easy, like when we want to just work on the EHS platform. Initially, when the session, one of the challenges which I told you when we were working in with the offline platform is the accuracy of the PWM generation. So this is what the main problem is. Sometimes it also gets overlooked because we might not actually go into this much depth. So what we'll try to do is if we study this particular picture over here, the right hand side. So these black lines, it represents the time steps where the data is being captured. So these black lines we can see that yes, this is the instance when the data is being captured. This is the instance when the data is being captured. Now, what we are trying to do is this particular triangle is the carrier wave for us, and this constant over here, this is this particular zero point 0.5 constant value for us. Now, what we are trying to do is we have kept a logic. You forget about what exactly these blocks are. What we are trying to just understand is like if these blocks are replaced by the normal SPS blocks, by the normal blocks which are there in the Simulink library. So what it will do is that whenever the value of 0.5 is greater than the triangular value, we'll have a logic 1. So if you try to see the result which corresponds to the Simulink, we see at the initial time when the time step first was there, the value of 0.5 was greater than the carrier 1, and we have our logic 1 over here. Now, if we directly come to the second time step, now again the logic is being compared, but this time the 0.5 value is less than the carrier waveform. So that is why our logic will get transferred from a value of 1 to 0. But you see, the actual process what would have actually been done is this value of 0.5, it has become less than the carrier waveform at this particular junction. But the thing was that since we were working with MATLAB and the calculation is only done at these time steps only, which are defined by these black dotted lines. So that is why Simulink is not able to capture the information between two consecutive time steps. That is why whenever we are working with the Simulink, uh, depending on the value of time steps which we choose, there might be a loss of accuracy on the PWM pulses which we are generating. Now the solution which we provide is that these blocks, if you see, these are the normal blocks which we all see in the Simulink library, but these are the Opal Artist library which is being developed. So that is why our sign is written over here, representing the RT events. So what exactly these blocks does is that if we open these blocks, it tells the user the information that how many moments you want to capture between these two instances. We say if what I'm trying to say is that between these two time steps, so let us just see that what I'm trying to do is I'm focusing on these two time steps. So what we are doing is, I mean, we can have any two time steps in fact, because the time remains the same. So within the RT event, this is the RT events block. So if we just open this RT events, there is this option called as how many events we want to capture. So we can have a maximum of from 0 to 255 events. What it means is that within two time steps, that how many events are we expecting? And because the carrier frequency is in our hand, so we might have a rough figure of the events which we want to capture. So let us say that I am saying the RT events, that I want to capture 4 events. So what it will mean is that between two time steps, it will have further 4 steps at which the data can be captured. Do you see how using the help of RT events, we are actually increasing the accuracy of the PWM generation? We can see, since we have a capability of having the number of events to be captured is 255. So in an indirect or direct way, I can say that the PWM pulses which we are generating from the RT events, it has 255 times higher accuracy than the Simulink one. One thing I'd also like to, pinpoint over here is that whenever we are working with RT events, so we see this is the result we have seen over here. So this is the RT events result we see. And corresponding to RT events, we can see that the logic, it is giving the very accurate answer. So one may ask is that whether the time step which we are doing in the RT events, because as I had told over here, that time interested in 4 values in between two time steps. So does it mean that initially, if I say that if my time step was say 10 microseconds, and now because I want to capture 4 events also in between, so does it make that my time step has now become to 2.5 microseconds? I mean, this is one very good question if someone like could have asked. But yes, of course, the answer to this is no. That whenever we are working with RT events, it will run at the same time step. So it will run at the 10 microseconds only. It is not going to run on the 2.5 microseconds. So this is like the beauty of it, that we are not like overburdening the computation power of the processor. It is just that the RT events toolbox, they detect the information which is getting changed from 1 to 0, 0 to 1, and that piece of information is only going to make the transition. That is why the RT events, they are able to like deliver us a higher PWM pulses without overburdening the processor, and that too, the degree of accuracy is 255 times more than the Simulink. So till now, I mean, what we have studied is the power electronic solution for the high switching frequencies which we provide. And since we are working with high predominant pulses, we need to make sure that yes, the pulses which are being generated, they are in fact of high accuracy. For that particular case, we have the RT with us. But as a last thing to the session is there is one more toolbox which we provide, which is called as Artemis. So what Artemis does is we'll be studying about this one. What it is called as Advanced Real-Time Electromagnetic Solvers. So if we like try to just understand that how exactly the Simulink models which are there in the MATLAB, how do they run? So the SPS approach is that it solves the electrical system using the state space approach. So in the space approach, there we all know that these are the two equations. So x bar equal to ax plus bu. So this is the equation which is going to determine the state of the system, whereas y is equal to cx plus du, it is going to determine the output of the system. Now, what exactly is being done within the SPS, I mean within the SPS is that let us say that for this particular model which we have in our example, we see there are two switches over here. So what it trying to do say is that as of now we have both the switches closed. So I mean open. So for this particular case, we will have a different. I mean, we will have one x is equal to ax plus. We will have one set of state space equation, right? Now assume that one switch is closed. That means again we will have a different state space equation. So in total, if we say that we have a total of two switches, we have four sets of state space equations. I think someone has a doubt in between, I guess. Does anyone have any doubt? Actually, I heard like some voice from them. Okay, I think it must be like by mistake. So what I was trying to say is that what SPS does is that depending on the number of the switches which are present in the model, we will have those many two raised to the power sets of equations. So for two switches, we have two raised to the power two, which gives us four sets of state space equation. Now this actually creates a problem. The thing is, if I just try to here. Now this is the if you see from this particular black dotted line. So this is your real time limit. So what it means is that initially, like I had told you, that when we have a real plant on the physical side and we have the simulator. Now from the real plant, we know that the information which I want to transfer is at 1 second, one sample per second. So we have a real time limit with us, right? Now the thing is, what we are trying to do is this particular MATLAB model where we have these switches getting changed. So with every change in switch, the topology changes. The MATLAB, what MATLAB needs to do is it needs to recompute the state space system equations. So it will require more time. So we see over here that in the red one over here, what we see is that whenever there is a change of topology, that means whenever a switch has changed its status from 0 to 1 or 1 to 0, sorry. So whenever the topology changes its status, the state space matrices it needs more time because the entire recomputation is to be done. So we see that the real time limit it has been closed, and this is one thing which we do not want because we are going for a proper testing of our algorithms and everything. If things happen, we might not be able to like. This is the main problem we are working with the SPS solvers. The problem also comes with the SPS solver is that the solver it uses is a Thurston solver. So if we see that if I like close my switch and open my switch, so if this instance we see at this particular instance at point 0.05, we have opened our switch, and the opening of the switch has led to a transient, as we can see over here. The reason is because the Tustin solver which is being used in the background, it is marginally stable, and because it is marginally stable, it is like prone to oscillations. We can see that how we are actually having these particular issues with us. And then the another issue with the SPS SPS solutions is that the accuracy of the system is also low, because the thing is the SPS uses a solver of order 2. So because it is using a solver of order 2, the value from the exact is a very different one. If we see that if we are trying to compute the value of e raised to the power 1, so the actual value is 2.71, whereas the value which we get from the SPS, which uses a solver of order 2, it is approximately 2.5. So we see that there is an accuracy issue as well also. Now the solution which we provide on the power system side is called as Artemis. So what Artemis does is the main thing, since we already know that we have two switches, and corresponding to these two switches we have four state space matrices. So what Artemis does is it is going to pre-compute and discretize the all state space matrices. So this means whenever the switch changes its states, it will get the entire information from the cache memory, and the time which was initially required will be less now. So if we see over here that initially when the switch was changing its state, we see that the red colored one, which was the SPS time, it crossed the real time limit. But when we work with the Artemis, we see, because all the state space matrices has already been computed, the time it is taking is far less than the actual time. I mean, it is far less than the SPS. The other benefits of Artemis is that Artemis uses a solver of order 5. So that means for a solver of order 5, it has higher accuracy as compared to the solver SPS solver, which has order 2 capability. And the last is that Artemis is also like more stable than the SPS library. So if you try to see the result, that if you try to like open the switch, and we see that the oscillations which initially were very high, they are like very less in this particular case. So this is like the benefit of using the Artemis solver over the SPS solver. Okay, I think just 5 left, so we can like devote those 5 minutes for the questionnaires if the participants have any. Uh, this is the entire information which I wanted to deliver from my end for this particular session.
Manik sir, we are not able to hear you.
Hello.
Hello. Yes, now
So,
it's audible.
okay. Since when did you lose me, sir?
Pardon? It's just I think 2-3 minutes ago. Two
Okay, I
minutes ago.
like. Can you just tell me from where should I start again?
Uh, exactly. You can go 2-3 slides back.
Okay.
Yeah,
So
from here you can.
okay,
Yeah,
I
yeah, from no, just earlier one. Can you go back a little bit? There is one red
can.
curve is coming into the.
Okay, this is over here.
No, 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 no. It's little bit later. Yeah, from
Yeah.
here.
Okay. So what we were actually doing is we were studying the effect of SPS libraries. I mean the SPS solution. So what we were observing is that whenever the switch changes its status, we see that the time which it requires is very high as compared to the real time limit. This is one of the drawback when we are working with the SPS solver. Apart from this particular time limit issue, there is an issue related to the stability as well. As we can see from this particular figure, that when the switch is being made to open at 0.05 seconds, we see that because since the solver is marginally stable, this particular topology, it is prone to oscillations, and we can see the similar results, that when the switch is opened at 0.05, we can see a high oscillation in the graph of the load voltage profile. And not only about the stability issues, we have problems related to the accuracy as well. So we see that SPS, it uses a solver of order 2. So what it means is that it is only going to take the first two parameters while evaluating the values of a constant. So we see that if we are trying to compute the value of e raised to the power 1, which gives us somewhere around 2.71 something. So if we see that if we are using SPS of if we are using SPS of order 2, we see that the value which we are getting is 2.5, and it is like we can see that there is an accuracy issue with this one. Coming to the solution which we provide is advanced real-time electromagnetic solvers, the Artemis solution. What exactly is being done in the Artemis solution is, since in SPS1 we have already seen that the reason why SPS takes more time is that whenever the switch changes its state, the SPS library, what it does is it is going to recompute the state space matrix, and that is why it takes more time. What Artemis does is, after the topology is being uploaded into the Artemis toolbox, what it will do is it will analyze the number of switches it has, and it is going to pre-compute all the state space matrices. Now, this state space matrices, this information is stored into the cache memory, so that whenever the state space matrices are required, they can be directly fetched from the cache memory. And this is the sole reason that Artemis uses less time as compared to the SPS. We can see over here that with Artemis, so whenever we have a change of topology, that is whenever a switch changes its status from 0 to 1 or 1 to 0, initially the SPS1, the one shown in red in color, it has a very high value, with the reason because every time the switch changes, the state space matrix is like it is going to again compute the state space equation. But with Artemis, since the information it has to be just fetched from the cache memory, so that is why the time which it takes is far less than the SPS one. Apart from this one, Artemis, it uses a solver of order 5. So what it means is, when compared with the SPS solution, it is going to be more accurate because it is using five parameters to solve the value of the various variables. And apart from the accuracies, the Artemis solver, it is also very stable. So as we can see that when now the switch is being opened and we are using the Artemis toolbox, you can see that the oscillations which were very high in the initial study, they are very less. So we can see that how the Artemis actually has enabled for a more stable system. So this was like all about the Artemis solution which we provide. If the participants they have any doubt, they can feel free to or even if like if you get to have a chance to work on the any of the OpenRT simulators, you can always contact us through the official website. There is this one link which you can go over and you can always fill the form and can reach out to us. Also, what you can do is just one second. I can even type in. I don't know how to type in my email ID. I could have given my email ID so that if anyone has any doubt, they could like contact us also for any help from my side. But since I cannot type it, it is Manik MANIK dot Jalhotra JALHOTRA @opalrt.com. Opal hyphen RT. You can always reach to us if in case you have any query. Thank you. Sir, this
Manik
is
sir?
all from my side.
Yeah, yeah. So let me check the chat box, please. Okay. So I would like to invite the participant if they have any query, and they can directly unmute themselves and ask with the speaker. They can discuss their query with the speaker. I'm requesting to the participant, they may ask their query to the speaker. They can, I have allowed them to unmute. Okay, meanwhile, I have one query, sir. Sir, like if is any one of the university want to implement some systems, so could you tell in at the time of proposals when we are submitting for the research grants, etc., could you help to get the estimate if we want to include the OPLIT?
Sure, sir. As I was mentioning in my session, it depends. First of all, it depends on the requirement because there are various products and various toolboxes. So if you are if you want to work on the power electronic side, then you need to go for EHS. But again, on EHS, how much power of the EHS you require? So once you decide
Okay.
all of those things, depending on the research criteria which you have, or if just as say that there is not a single research criteria because there will be say your PhD, MTech people, they'll be working on it and it is an open playground. So we can go for the generalized solution and the and proper cost of these things. This is where the sales people they will come into picture and they can give you the best quoting of this real-time simulators. So I can
Okay.
forward the details to you so that if you want, you can contact them.
Okay, thank you very much. I think there is no question from the participant side. So with this, thank you very much for being with us, sir. And give me,
Thank you for inviting.
so this is e-memento from our side. Please accept it, sir.
Thank you, sir. Thank
And this is a certificate of appreciation.
you very much.
Thank you.